Okay, guys. Last time we covered the second order response, and we covered the situation where we defined some constants within the response equations, mainly the undamped natural frequency and the damping coefficient. And we covered the case where the damping coefficient is larger than one. This is what's called the overdamped case. And then we covered the case where it says zeta. Yeah, zeta is less than 1. This is called the under damped case. Right? And then what remains is covering the case where zeta is equal 1. When the damping coefficient equals 1, this is called the critically damped case. It's at the borderline between being overdamped and underdamped. So it's the borderline between showing mainly exponential behavior in the case of overdamped, and underdamped shows like oscillatory behavior, right? So it is kind of like the in between case. It's the borderline case. So if you look at a response of the system, when the system is overdamped, it might look something like this, and then it becomes less damped until it hits a point where it's critically damped, and then if you go beyond that point, the system starts to get oscillatory a little bit. Okay, and then if you become more and more underdamped, the system gets more oscillatory. Okay, the critically damped case requires special treatment. Why? Because remember we said that the characteristic equation for the second order system or equation has two natural frequencies, lambda 1 and lambda 2. Lambda 1 is minus zeta omega naught minus omega naught zeta squared minus 1. Yeah, this is the first natural frequency. The second natural frequency is minus zeta omega naught plus omega naught zeta squared minus 1. Right. So this is the two natural frequencies when zeta is larger than 1, right? When the system is overdamped, right? So what happens as zeta gets closer to 1? So what happens when the zeta gets closer to 1? As we keep approaching 1 and getting closer to 1, this term and this term approach 0, right? So that means that as the damping coefficient approaches 1, lambda 1 approaches lambda 2, or we get to a point where lambda 1 equals lambda 2. So something happens. We have two solutions, right? E lambda 1t, E lambda 2, two distinct solutions. As we approach 1, those two solutions get closer to each other until we reach 1. When we reach 1, one of the solutions, we end up collapsing the solution space, meaning instead of having two distinct solutions, suddenly we have one solution, E lambda 1 or 2, right? It's the same. E lambda 1 or lambda 2 becomes the same. So we end up collapsing the solution space from two dimensions, two distinct solutions, to one distinct solution. So this sort of phenomena is called ill conditioning. It becomes an ill-conditioned system, right? And why is that a problem? Well, that's a problem because according to ODE theory, second order differential equations, all general solutions of second order differential equations are built from two solutions. So you have two solutions, E lambda 1 t, E lambda 2 t, and this is the two basis solutions that you solve for when you solve the characteristic equation, and then the general solution is built from those two solutions. It has the form E lambda 1 t plus k2 E lambda 2 t, right? So that's a fact. You need any second order ODE will have two distinct solutions. And you can build the general solution from those two distinct solutions, with a homogeneous equation. What happens for the case where eta goes to 1, what happens is that one of the solutions, the two solutions, distinct solutions, combine with each other, and we lose one distinct solution. We end up with only one distinct solution. So we don't have enough to build the general solution, right? Because it doesn't, even if eta equals 1, doesn't change the fact that the second order equation should still have two distinct solutions. That fact is a theory in differential equations that will not go away, regardless of the value of the constants in the characteristic equation. We should always have two distinct solutions to build the general solution. Right? Our method gave us two distinct solutions when eta was not 1, but when eta approaches 1 and gets to 1, we lose one of the distinct solutions, and we need to figure out a way of getting another distinct solution to get the distinct solution to get the general solution. There are many ways of doing that, but mainly the trick is as follows. So this is, let's say this is the z-plane, complex plane, right? There are many ways of doing that, but the trick is as follows. We take the general case where we have the two solutions are on the real line, and we assume that what happens when eta approaches 1. The two solutions, right, lambda 1 and lambda 2, get closer to each other. This term and this term approaches become closer to 0. 1 minus 1 is 0, right? So those two roots of the characteristic equation approach each other until they go on top of each other, right? Same thing if we had two complex solutions. We could approach this problem from the underdamped side or from the overdamped side. From the underdamped side, the two roots are gonna get closer to each other until they come on top of each other, right? The key is to examine what happens as the roots get closer to each other. Can we do an approximation before losing the other solution that will allow us to kind of like guess or figure out what a new distinct solution is going to be, right? So let's do that. So like I said, we can approach, right? So the case where eta equals 1 is like two solutions for the characteristic equation on top of each other in this way. We can approach it as two solutions hitting this point, right, approaching each other, and then until they're on top of each other. So this is starting with eta. This is starting with the overdamped case. So this is starting with eta larger than 1, and then eta approaches 1. Or we could examine this from this point of view. We have two solutions that are complex conjugate, as we figured out last lecture, right? And then we get closer and closer to the situation where the two roots are on top of each other on the real line. So this is starting with eta less than 1, the underdamped case, and then taking eta to go to 1, making eta approach 1. Right? So this is easier to start with. I'll start with this. Okay, I'll use this. Okay. So in this situation, the two distinct solutions for the second order equation, we found them to be as follows: E minus zeta eta omega naught minus omega naught zeta squared minus 1 t. Oh, this is zeta. This is eta. So this is eta. So this has to be zeta. Okay, now I remember. So this is one solution, and then the second solution is this E minus zeta omega naught. We've discovered this last lecture. Plus omega naught zeta squared minus 1 t. So I'm examining those two solutions from this point of view. The two solutions are on the real line, and then I examine the situation where zeta is approaching 1, meaning the two solutions are getting close to each other. Okay, I want to examine, so what happens if zeta equals 1 exactly? Those two solutions lose their distinctiveness. They become a single solution, right? They become, they turn into, if I naively just plug in zeta equals 1, I end up with one solution, E minus zeta omega naught t. I don't want that. This is, I want to try to kind of extract out another solution on top of this one so that I can build a general solution. Right? So I have to use the fact that those two roots are now close to each other, and I want to see if I can apply an approximation to the exponential function so that I can deduce what the distinct solution is. Okay, so those two are solutions. As the two roots are approaching each other, those two remain solutions. And I can take any number of solutions, sum them together, and I'll still get a solution. So I can state factually that this is also a solution, what I'm going to write down now. So just summing those two together and dividing them by some constant of my choosing. If I sum those two solutions together and multiply them by any constant, I divide them by any constant, I still get a solution. That's a fundamental fact in differential equations. So let me sum those two solutions together to get another solution and then divide by some constant of my choosing. Right? So this is going to be E minus zeta omega naught minus omega naught square root zeta squared minus 1 t minus E minus zeta omega naught plus omega naught zeta squared minus 1 t, and then I want to divide it by a constant of my choosing. I'm going to choose a special constant that it will be apparent why I chose that constant later, but it's just a matter of choice. I can choose any constant. I'll choose the special constant. I'll choose 2 omega naught zeta squared minus 1. Yeah. So this is a peculiar constant to choose, because what happens now is if zeta approaches 1, the denominator becomes what? 0. So I end up with like right. So what happens here when zeta approaches 1? I end up with this thing, E minus zeta omega naught t. This thing cancels because 1 minus 1 is 0, and then minus E minus zeta omega naught t. So I end up with 0 over 0. Right? So to find what this thing is going to be as zeta approaches 1, I need to take the limit. Because if I just plug in zeta equals 1, I get 0 over 0, which is nonsensical. Okay, so I need to do now, to find the limit, I need to do an approximation. I need to approximate the exponential. But first, let me do this. Let me take this exponential out of the expression. Right? How do I do that? Okay, so I'll do that now. By the way, I had to re-record this portion of the lecture because again my microphone is giving me trouble again. Sometimes it works fine, sometimes I get a lot of clicks in the recording. I'm not sure if it's an adjustment of gain. I tried to adjust again. It could be a software thing. So yeah, I'm still trying to debug that. I know, I mean, bear with me. I know it's annoying sometimes when you hear clicks, but I'll try my best to avoid those technical glitches. Okay. So yeah, so we said we wanted to kind of combine those two solutions to try to try to get a solution that becomes like get a distinct solution, right? That allows us to solve the general differential equation. Because we said, remember we said when zeta approaches 1, those two solutions get close to each other, they become the same solution. Right? Is there a way we can kind of examine them and find something, extract from them another solution that will be useful for solving the differential equation under those conditions, under the condition where zeta equals 1, right? So Right? So what we did, we said, hey, let's combine them and divide them by a certain constant. And let's manipulate this. Let's manipulate this a bit. So I want to manipulate this in this way. I want to take this term out of the numerator. So when I take it out, I end up with this expression, and then I end up with 1 where I took this out, right? And then I just end up with the opposite, the negative of that expression. So think about it. If you bring this in back into this bracket, you end up with the same expression. You end up with e minus blah 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 minus e minus blah 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 e plus. You use the property that EAB equals EA plus B. So those two cancel each other, and we end up with E0, which equals 1. And then we have E minus, which is the original term. Okay, so this has that form. This expression has this form. Now what we want to do is we kind of again use this property by summing up those two exponents. Right? When I do that, I end up with this expression. So I end up with e minus 2 omega naught zeta squared minus 1 t. Right? And here here is where I want to do the approximation. Right? I want to approximate now this expression, and I want to utilize the following approximation as x, any exponential ex. Remember, we discussed this, I think, we discussed this in lecture 3, maybe, perhaps, or 4. I don't remember exactly, but we said, hey, any exponential function, we can approximate it in a region close to 0 by a line segment, right? And the approximation is as follows: 1 plus some slope x. And for the exponential function, that approximation is 1 plus x. So we know that. We know that for small values of x, we can approximate e to the power x as just 1 plus x. Right? So that's what I want to do here. I want to take this term and I'm going to approximate it as 1 plus the exponent. In this case, it will be 1 minus 2 omega naught zeta squared minus 1 t. Right? So I do this approximation, 1 minus plus, right? So there's a minus sign here, so minus becomes plus. Right? And I do a cancellations, and then I get something here that's equal to 2 omega naught zeta squared minus 1, which cancels the denominator. Right? So this is exactly why I picked this particular denominator when I built this new solution, so that I can easily cancel out this term. Right? So all this gives me this solution, t times e to the minus zeta omega naught t. This is the additional solution that I'm looking for. So as the two roots of the characteristic equation become equal, they merge into a single solution, right? But from and I lose the second solution, I only have now one solution, but from examining what happens as the two solutions approach each other, I can extract another solution that substitutes the solution that I lost. Right? So lambda 1 and lambda 2 as zeta approaches 1 merge into a single solution. But by examining what happens to those two solutions as they approach each other, I can extract another solution that I can use to build the general solution for the second order equation, because differential equation theory says that the second order equation, ODE, needs to have two solutions that you can use to build up the general solution. You cannot just build up the general solution from one solution. You cannot, according to differential equation theory. You need two basis, what's called basis solutions, to build up the complete general solution. Okay? So all our manipulations led us to those two distinct solutions. Right? Here I'm kind of like zeta. I mean, I know zeta equals 1, so I don't need to put zeta here. Right? So the complete general solution becomes this. It becomes k1, some constant, e minus omega naught t, this term, plus k2, this other distinct solution that we found out, which is k2 Te minus omega naught T. Okay, so this is how we deal with for the case where the characteristic equation gives us repeated solutions, meaning we have lambda 1 equals lambda 2, and this occurs when zeta equals 1, right? This is how we deal with it. We take this merged solution, those two distinct solutions turned into one merged solution. We take that gives us our first basis for the general solution. We multiply it by t to get our second basis for the general solution, and we build our general solution, right? And this is only for a single case, for zeta equals 1. We know how to treat cases where zeta is larger than 1 and zeta is less than 1 already. This only covers the single case. All right, so this is the whole theory of second order response, second order differential equations, ODEs, and their solutions, and second order transients. Now is the time to do some examples. All right, let me quickly check the audio quality and see if I resolved the microphone issue, and we will continue with some examples. Okay, this is much better, not as much pronounced clicks as I had previously. This is still a weird problem because, like last semester while doing the EM theory class, I had exactly zero audio problems. I think it's one of those things where Windows updated recently, and it did something to the audio drivers, which is annoying because this happened to me multiple times where Windows update forces me to update, and then it changes something in the system. It introduces new problems into a system that was working perfectly. But anyway, that's neither here or there. Right, so I want to go back and solve some examples. First, I want to go through the problem solving. Remember how we approached first order circuits from a methodical approach. We described concrete steps that you need to go through to solve any first order circuits. So in the similar way, the author describes 5 steps to handle second order circuits, and those are logical steps. So of course, first you have to write the differential equation, right? And then the other step, which is different now, we're solving the equation using the characteristic equation method. So the second step is to write the characteristic equation that corresponds to that differential equation, and that's allowed us to deduce what omega naught is and what zeta is. Zeta directly tells us what kind of response we will get, right? So that's step 3. From zeta, we can tell if the response is going to be underdamped, overdamped, or critically damped. And we also need to solve the characteristic equation to find the roots of the characteristic equation, right? So that we can write down the solution. That's not necessary because the way I mean, it's good to find the roots, to find the natural frequencies, but all we need really is zeta and omega naught, if you think about it, because we derived the final forms of the response solutions in step 4 here. We know what the forms of the solutions is going to be dependent on the kind of solution, type of response. So we know for in the overdamped response, we just have to do K1 plus K2 with 2 exponentials, right? So we already know how to get the roots from zeta and omega naught. So in many ways, zeta omega naught minus omega naught square root zeta square minus 1 is the first root, and zeta omega naught plus omega naught zeta square minus 1 is the second root. So we know how to get the roots directly from zeta 1 and omega 1. This is analogous to using the quadratic equation to find the solution or find the roots. right? We know how to deal with critically damped. We have one situation, we have one root, which is zeta omega naught, but then we have to have another solution, tag it along with T added, right? And then we know how to handle the underdamped condition. Turns out to be a cosine and a sine with an exponential envelope, something like this. Would be a cosine with an exponential envelope. So it could be dwindling like this. It could be growing for under certain circuits, right? That wouldn't happen for real circuits because all circuits will have resistors that will dissipate the energy in the second order system, right? But it will have, the solution is going to have this form with cosines and sines, and where we have defined new constants sigma and omega d. Omega d is what's called the natural frequency, while omega naught was the undamped natural frequency. And this is how we find omega d. It's just omega naught square root 1 minus zeta squared, and then sigma is the exponent of the exponential envelope, which is just zeta omega naught. Okay? So we know how to get the form of the solution. And then finally, we need to find the constants. And we find the constant, because this is a second order equation, we need to apply two initial conditions. Those two initial conditions could be either x at the variable at 2 points in time, at xa and xb, or we take x at a and dx by dt at a. Right? So any two initial conditions, whether the value at a point and the slope at a point, or the value at 2 points, is enough for us to completely determine the two constants k1, k2, b1, b2, or a1 and a2. I'll do example 7.7 from the textbook, and this is an example that includes a parallel RLC circuit. So I have a resistor, I have an inductor, and then I have a capacitor. I could have a source if I wanted, a current source, but in this example, this is an example of a circuit that does not have any forced sources, right? So this still will have dynamics, right? Because if there are some initial conditions, for example, if the capacitor has some initial condition on it, the circuit is still going to have a transient, and it's going to go through a transient until things settle down. Okay, and then we solve for v of t. Okay, so we want to write the differential equation for this RLC circuit, and I think we did that last lecture, but that's fine. Let's redo it. So we use KCL. So we sum the three currents going into the inductor, capacitor, and resistor. So we have V over R plus, what's the current going through the inductor, right? VL equals L di by dt. So the current going through the inductor is going to be, this is IL. IL is going to be 1 over L integral from some initial time to some time of VL dt, plus some initial condition. There could be an initial condition in the inductor current. The inductor current doesn't need to start at 0. It could start at any value. Of course, this is not at 0, at t0. I'm considering my starting time to be t0. Okay, so I plug that in. I end up with 1 over L VL dt plus IL0. This is the initial t0. This is the initial condition, plus the current going through the capacitor, which is easy, which is C dV by dt. Right? The capacitor voltage is the same as Vt. Right? This equals 0. In this case, there is no forcing function. The equation that we want to solve is naturally a homogeneous equation. because it's a homogeneous equation because there are no sources in the circuit. Okay, so I differentiate this again. I get C d square v over dt squared. This constant, when I differentiate it, it becomes 0. This integral, when I differentiate it, differentiation is a inverse of integration, so I end up with VL over L, and then I end up with dV over dt 1 over R equals 0. Divide everything by 0 and rearrange. I end up with d square V over dt squared plus 1 over RC dV over dt plus V over L. Let me call this just V equals 0. Okay, so this would be the differential equation describing the parallel RLC circuit. Right? We already put the second order equation in a certain form with some predefined constant. How did we describe the second order equation? In general, we describe it as, for any variable, as d square x over dt squared plus 2 zeta omega naught dx over dt plus omega naught squared. Oh, there is a c here. Okay, so we can directly link those constants, circuit constants, to the general second order equation constants. Right? So this clearly shows me that omega naught should equal 1 over square root LC. This is the undamped natural frequency. And then 2 zeta omega naught equals 1 over RC. Right? So this is interesting. Let's manipulate this a bit. This equals 1 over. Let me manipulate this a bit. Let me multiply by L over L. So I end up with L over R LC. I didn't change a thing, just added that L in the equation. Now 1 over LC is what? 1 over LC is just omega naught squared, right? Omega naught is 1 over square root LC, so 1 over LC is just omega naught squared. So I end up with 2 zeta omega naught. Let me put this under a box. Equals L over R omega naught squared. Omega naught cancels with 1 omega naught here, so I end up with 2 zeta equals L over R omega naught. What's omega naught? Omega naught is 1 over square root LC. Square root L goes with square root L. I end up with 1 over R square root L over C. Right? So I end up with the zeta, the damping coefficient, being equal to what? To 1 over R square root L over C. Okay, there's a 2 there. Sorry, there's a 2 there. Okay, so this is the damping coefficient. This should be the damping coefficient. I think in the textbook there's an error there. Right, and how do I instantly know? So they say in the textbook it's damping term is half RC. Right? How do I know instantly this is an error? I know instantly this is an error because RC we know has units of seconds. Right? The damping coefficient cannot have units of seconds. The damping coefficient, if we examine our differential equation, omega naught has units of radians per second squared, right? Second, radians is dimensionless. It's just an angle. Radian is just the circumference of an arc of a circle over the whole circumference. So it's a length over a length. So radians is unitless, dimensionless. So this has 1 over second squared. Omega has 1 over second times 1 over second gives me 1 over second squared, and this is 1 over second squared. So everything, all the units in the differential equation need to be 1 over second squared. So the damping coefficient needs to be unitless, dimensionless. It has no dimensions. So this cannot be just half RC, right? It has to be this. From direct comparison, the damping coefficient is just this term. So this is an error in the example. Be mindful of that. When they say the damping term is half RC, that's an error. Okay. All right. So again, like I said, we can always check the units. So I said omega naught is a frequency. It's 1 over it's rad over second. So I should expect square root L over 1 over square root LC to have units of seconds. Sorry, units of 1 over second. Is that true? Again, let's check, right? So we know that VL equals L di by dt. So the units of L are what? Are volt from this equation. Are volt second. I take the dt to the other side over current amp. And then I know that I equals C dV by dt for a capacitor. So the units of capacitance is what? It's amp second over volt. Okay, so the unit, let me do this here. So the unit of LC is going to be the unit of V, volt second over amp, times the unit of C, amp second over volt. Volt cancels with volt, amp cancels with amp, right? I end up with what? Second squared. So 1 over square root second squared is 1 over second. So it makes sense. It makes sense for 1 over square root LC to be a unit of frequency because it has units of 1 over second. And as we said, radians is a dimensionless unit. Okay. In contrast, now this has to be dimensionless. This is just a coefficient. It shouldn't have any dimensions. Let's check that. So the units of zeta are going to be square root. So they're going to be the units of R. What are the units of R? Units of R are, this is zeta. Unit of R is, well, the inverse of R. Unit of R is volt over amp, right? So it's going to be amp over volt. Square root, what's the unit of L? Unit of L is volt second over amp divided by unit of C, which is amp second over volt. Let me rewrite this, amp over volt, square root volt second over amp times, I invert this when I take it to the numerator, so this becomes volt over amp dot second, right? I end up, second cancels with second, and I end up with amp over volt, square root volt squared over amp squared. This equals amp over volt times volt over amp. Aha, so this is dimensionless, as we expect. Okay, so for this circuit, omega naught is going to be 1 over square root LC, and zeta is going to be 1 over 2R square root L over C. Okay. Now, example goes and gives me specific values for the capacitor and the inductor and the resistor, and asks us to solve the equation and get the second order response. So it gives us inductance of 5 Henry, capacitance of 1/5 farad, and resistance of 2 ohms. Okay. Before continuing, I think I missed something here in the equation. Oh, okay, this is what I missed. So the equation is, there should be an x here equals 0, right? So it's not omega naught squared, it's omega naught squared times x. Okay. So let's do the example for those coefficients, for those values for the circuit parameters. The other parameters that we need also are the initial conditions. So the given initial conditions are as follows: I L at 0 equals -1 amp, and I VC at 0 times 0 equals 4 volts. Okay, so we said that omega naught equals 1 over square root LC. So this is 1 over square root L is 5, C is 1 over 5, simple. Omega naught is just 1 radians per second square. Okay, zeta is 1 over 2R square root L over C. So this is going to be R is 2, so it's going to be 1 over 4 square root 5 over 1 over 5. We end up with 4th square root 25, which is going to be 5 over 4. Okay, so notice that zeta is equals 5 over 4, which is larger than 1. So what does that tell us? This tells us that this is an overdamped circuit. So we should expect the response for the state variable V to have this form. It should be some constant K1 E minus zeta omega naught minus omega naught square root zeta squared minus 1 T plus K2 E minus zeta omega naught plus omega naught square root zeta squared minus 1 T. So let's calculate those terms, those exponents here. So this is going to be, we said omega naught is 1, zeta is 5 over 4, so this is going to be 5 over 4 minus 1 square root. Zeta square is 25 over 16 minus 1. Instead of 1, let me plug in 16 over 16. This gives me 5 over 4 minus, what's 25 minus 16? That's 25 minus 10, 15, minus 6, 9, 9 over 16. All right, so this is going to be 5 over 4 minus 3 over 4. The first exponent is going to be 2 over 4, which is half. Let's do the second exponent. It's going to be 5 over 4 plus, it's the same thing, right? Omega naught zeta squared, square root zeta squared minus 1 is going to be the same thing as we found here. So it's going to be plus 3 over 4. So it's going to be 5 plus 3, 6 is 8. 8 over 4 is going to be 2. So the second exponent is going to be 2. Right? So the form of the solution is going to be Vt equals K1 E minus half T plus K2 E minus 2 T. Right? So we need to find K1 and K2. We need to apply two initial conditions. We're given two initial conditions. The first initial condition directly can be applied. So this tells us that t equals 0, e to the power 0 is 1, right? So it tells us that K1 plus K2 equals 4. Okay. We need to apply now this second initial condition. We could have had dV by dt, but we don't have that. What we have is the inductor current. So we need to go back to the circuit. So we have R L C, and see how we can relate extract the second initial condition from the inductor current. So this is I0. Okay, we need to kind of apply KCL again, right? Because we know what the voltage is on the cap. This is V of t. What is the voltage on the inductor? What is the current through the capacitor then? So IC is going to just be C dV by dt, right? So that tells me that IC is going to be, and C, what is C? C is, in this case, C is 1 over 5, right? So this is going to be equal 1 over 5. And then what's dv by dt? It's this expression. We just have to differentiate it. So we end up with minus half k1 e minus half t. This is how we differentiate an exponential. And then minus 2 k2 e minus 2t. Okay, so this is 1 over 5. So this is going to be minus IC is going to be minus 0.1. 5 times 2 is 10. Minus 1 over 10 is minus 0.1. K1 e minus half t minus 2 over 5. Well, 2 over 5 is 4 over 10. So this is minus 0.4 K2 e minus 2t. And then finally, we apply KCL to the circuit. We know that IL plus IC plus V over R, which is R is 2, V over 2 equals 0, right? So that tells me that IL equals minus IC minus V over 2. We already have IC. IC is this expression, so I end up with 0.1. Is this right? Yeah, this should be right. So this should be Did I make a mistake? Yeah, no, I think this is right. So this is, we end up with so we calculated V already, right? And then we differentiated V to get I, right? And then C is 1 over 5. This is the key thing. And then I plug the 1 over 5 in. I end up with minus 1 over 10.1 and minus 2 over 5, which is minus 4 over 10. Okay, so this is correct. All right. So minus 1 IC is going to be 0.1 K1 E minus half T plus 0.4 K2 E minus 2T, and then minus V over 2, which is minus half. V is K1 E minus half T, right? So we calculated V here. We just have a factor of half minus half K2 E minus 2T. So the total IL is going to be 0.1 minus 0.5 is going to be minus 0.4 K1 E minus half T, right? And then 0.4 minus 0.5 is going to be minus 0.1 K2 E minus 2T. Now we know IL0 equals minus 1. So I can plug this in here in this equation, and e to the power 0 is going to be 1. So I end up with minus 1 equals minus 0.4 K1 minus 0.1 K2. Let me multiply this whole equation by 5. I end up with minus 5 equals minus 0.4 times 5 is what? 0.4 4 times is going to give me 1.6 plus a final 0.4 is going to be 2. So it's going to be minus 2 K1 minus half K2. So this is the second equation. So I end up with two equations I need to solve to find K1 and K2. I end up with K1 plus K2 equals 4 and minus right, K1 plus K1 right, oh yeah, and minus 2 K1 minus half minus 2 K1 minus half K2 equals minus 5. right? So let me solve this equation. So what I can do, because I want to kind of like solve this system of equations, let me multiply the second equation by 5, but by 2. So I end up with minus 10 minus 1 minus 4. This allows me to cancel the K2, right? So this becomes minus, the K2 cancels, and I end up with K1 minus 4. K1 becomes minus 3K1 equals minus 10 plus 4 minus 6. So that tells me K1 needs to be equal to 2. K1 plus K2 equals 4. So that tells me also that K2 equals 2, right? And this is the solution. This is V of t. V of t is going to be 2 e minus 2t plus 2 e minus half t volts. I put the units in brackets, okay? And this is the solution. Say they ask you also for IL. Let's say they ask you for the inductor current. Well, the inductor current is just going to be 1 over L, the integral of the voltage dt. That's what the inductor current is going to be, and we can easily calculate that from there, right? So that's going to right? So that's going to be of course, you have to remember we have the initial condition plus IL 0. So this is from 0 to t, right? So we have to remember that. I think the book omitted that, right? So you have to be mindful that the inductor has an initial condition. But this is just a matter of integrating this expression. So this is going to be L is 5, right? So it's going to be 1 over 5. We know how to integrate exponentials. So this is going to be 2 e minus 2t over minus 2. That's how you integrate an exponential. Plus 2 e minus half t over minus half, right? Plus the initial condition, which is minus 1. So this is going to be 1 over 5 minus e minus 2t minus 4 e minus half t minus 1. This would be the inductor current. Okay. If you plot, let's plot. So what was the initial value for the voltage? Initial value for the voltage was 4 volts, right? That was what was given, 4 volts. So if I want to plot V, I start with initially before t equals 0, I am at 4 volts. Should V be continuous for the voltage or not? V should be continuous because the voltage across the capacitor should be continuous. So if we have the voltage here at t equals 0, it should give us 4. And it does. 2 plus 2 is 4. So we still start at 4, and then we have the exponential that's decay. It's not a single exponential. This has 2 exponentials in it. So this will look like actually let's draw it here now. So the response is actually a sum of 2 exponentials. That's why it's a second order system, not a fourth order system. So this is V, right? And then we have the sum of 2 exponentials. So we have the first exponential, it has a time constant of 2, right? So it takes it has a the response is like this, e t over tau. So the time constant of this first exponential is what? Is half. Tau 1 is half a second, right? So the first exponential decays faster. It has a time constant of half. So this is, let me draw the first exponential. It's like something that decays within half a second. It reaches 63% within half a second. The second exponential has a time constant of what? Of 2 seconds. So it decays slower. It decays four times slower. So the second exponential is something that decays 4 times slower. So it's much slower. So okay, and those two actually start at 2, not at so this is 4. They start at 2. So this is the first exponential. It decays. And we erase everything. It decays fast. Starts at 2, decays fast. The second exponential starts at 2 and decays much slower. And when the response is going to be the sum of those two exponentials. So initially we'll be decaying fast, but then the decay is going to peter out, and it's going to look like there are two exponential curves superimposed on each other. So the response is going to look something like this. Sometimes it's easy to discern that there are two time constants involved in the total curve. Sometimes it's harder. I think this is the case where it will be a little bit easier. Okay. So, okay, I would like to kind of like do computer-aided plotting of this response curve that we derived. I want to see if we can easily discern the nature of the second order response. This is not an oscillatory response. This is a response that has two exponentials of different time constants. So I'm saying that sometimes it's going to be easy to tell, sometimes it's not. Let's see if this is one of those cases where it's easy to tell. So we want to plot. I guess I can, let me try to expand the font. Right, so we want to plot the total, which is 2exp. The exponential function has capital E, I think. Yeah. And then minus 2t minus 2t, and then plus 2exp minus half t, and let me take t from 0 to I don't know what's a good value, maybe 5 seconds. Okay, so this would be the curve. So yeah, it's kind of like hard to tell if this is a single exponential or two exponentials, but it is the sum of two exponentials. Let's actually separate. Let's try to see if we can plot the exponentials separately along with the curve. So the first one is the exponential with the half a second time constant. This is the fast exponential. So I think for plot range, I need to make sure that the plot range is full. Okay. All right. So this is the fast exponential, and then there is the slower exponential, which has a time constant of 2 seconds. Yeah. So you can see the green line is the much slower exponential, and the sum of both of those is going to be the blue curve. Notice how after a very long time the slower exponential becomes dominant. The other one already decayed to 0 and does not factor in anymore. So you can almost see it. You can almost see it where this thing is going down fast, right? But then it's slowing down. The decay is slowing down. Actually, a better way to see it is to compare, let's take the fast exponential, which is this one. This is like a first order exponential, first order response, and then let's scale the slow exponent, fast exponential, so that it has the same magnitude. So that's the best way to compare two responses, is you have to compare them at the same magnitude. So let's multiply this by 2 to start at 4. Okay, and now you can see it. You can see that this is actually being slowed down by the slow exponential. Let me also compare this. Take 2 minus 1 over half. So this is 1 over 2. So this is the slow one. Okay. So notice. So here I scaled both of them. I scaled the slow response, and then let me scale the fast response component of the response by 2. So you notice our response lives in the middle. It is between the fast response and the slow response. It is a sum of those two. It is slightly faster than the fast response because of it's a combination of two responses, and it's slightly slower than the slow response. It lives in the middle between them. That's interesting. All right. Yeah. Okay. So with that, we're gonna finish this lecture and continue with more. So according to the schedule, we should be done now, but I still want to take another lecture and do some more examples. I think that would be helpful. And then also we will do like some problems and homework too. So that hopefully will give you enough exercise to kind of have this solving second order equations or systems as part of your skill set. All right, thank you guys.